In the second video, we're going to take a look at the periodic table and emphasize some vocabulary and some important history with the periodic table. First of all, we notice here that the periodic table was invented in 1869 by a Russian fellow named Dmitry Mendeleev, and you do need to know his name. There were actually several different scientists who were playing around in the early 1800s with organizing the elements in some meaningful ways, but history has given Mendeleev credit with a layout, an arrangement that is closest to our modern periodic table. Keep in mind the date, 1869, is about 30 years ahead of the discovery of the electron, ahead of the discovery of the nucleus and protons. So at this point, Mendeleev really had very little to work with. What he did was take a bunch of cards, like index cards, and he put on each card the name or symbol of a known element at that time. Remember, at this time, there were lots of elements that we now know of that had not yet been discovered. On these cards, he would write different chemical and physical properties, things like melting points and densities and boiling points. He also knew pretty roughly for most of the elements some atomic masses. And one of the first things he did was he realized that maybe he should order the elements from the lightest atomic mass, hydrogen, up to the heaviest atomic mass. Notice that our modern periodic table doesn't quite arrange the elements in the same way. We organize it according to atomic number, the number of protons in the nucleus. If you look at a modern periodic table, you'll notice that although it's pretty much still in the order of atomic mass, if you look closely, you'll find several spots, 2 or 3 spots, I think, where that doesn't follow. So our modern table is arranged based on atomic numbers. But remember, Mendeleev didn't know anything about protons or atomic number at this point. He also, so physical properties, chemical properties, atomic mass is what he had on each card. After arranging them from lightest to heaviest, he then grouped the cards according to similar physical and chemical properties. For example, he knew that helium and neon and argon, these elements which we now put over on the far side of the table, they're all chemically unreactive and they're all gases at room temperature. So putting them together made sense. By rearranging the cards in different ways and grouping them together by chemical and physical properties, he came up with an arrangement very close to our modern periodic table. So he gets credit for the discovery of the periodic table. It's absolutely amazing that he was able to do this and match the modern table with our current understanding of atomic structure. He got it right about 50 years ahead of time. When you look at a periodic table, one of the basic ways to organize the elements is according to metals and nonmetals, and they're separated from each other by a heavy line on the right-hand side of the table, okay, underneath boron, and it basically makes a staircase pattern like this. And everything on the left-hand side of that staircase are metals, with one exception. Over here, hydrogen is put in that column because it has one valence electron, like everybody below it. But hydrogen is not a metal. Hydrogen is actually a non-metal, and nonmetals are on the right-hand side of that staircase. Down here at the bottom of the periodic table, there's 2 sections which aren't shown here. These are also metals. So you can see that by far most elements are metallic, very few are nonmetals. Now, along that staircase, and technically along the right-hand side of it, the elements that touch along the right-hand side of that staircase, they sometimes share properties of metals and nonmetals because they're right in the middle. They're referred to as metalloids or semi-metals, okay? So if you're on the right-hand side of that staircase and touching the staircase, you may end up having properties of both metals and nonmetals. The properties of metals, they're shiny. The fancy word for that is lustrous. Okay? Now sometimes they may not appear that way because they've corroded. An old penny will look dark and grungy, but if you drop it in some vinegar, it'll dissolve the grit on the outside and reveal the nice shiny brand new copper underneath. Metals are also relatively soft, and often they have to be heated to reveal that, but when they're soft, you can do two things. You can take them and hammer them into a sheet. That hammering into a sheet reveals their malleability. They're malleable because they can be hammered into a thin sheet. You can also pull on the two ends of a hot metal and stretch it into a wire. So being able to be stretched like that into a wire is referred to as being ductile. Metals make good conductors both of heat and electricity. And as we saw earlier, they tend to form cations. They tend to lose electrons. So those are 1, 2, 3, 4, 5 properties of metals that you need to know. Note that many students want to say that metals are also magnetic. That's not actually always true in the way we normally think of the word magnetic. Only iron, nickel, and cobalt are magnetic in the sense that they can be formed into magnets, or that they'd be attracted by a magnet. Okay? Now, nonmetals, their properties are pretty much the opposite of the metals. Instead of being shiny, they're dull. Instead of being soft, malleable, and brittle, if you tried to hammer a nonmetal, or if you tried to pull it into a wire, it would basically shatter or snap because they're brittle. They don't conduct electricity or heat, so nonmetals tend to make good insulators. And instead of losing electrons, they tend to gain electrons, so they become anions instead. The semi-metals, or the metalloids, have properties of both of these things. For example, carbon is found right near that staircase in the second row of the periodic table. A piece of graphite, pencil lead, is actually made of carbon. And you could argue under certain conditions that it has a certain shine, a certain sheen to it. So you might argue that it's lustrous. On the other hand, I think you'd agree a piece of pencil lead, if you tried hammering it or stretching it, it would simply snap. So carbon, although it's shiny, is also brittle. The carbon can be used actually as an electrode in a battery because it conducts electricity. So it's actually a pretty good conductor of electricity. So carbon, in the form of graphite at least, has properties of both metals and nonmetals, making it a metalloid or a semi-metal. Silicon is another really good example of that in a similar way to carbon. When you look at the periodic table, we'll go a little bit deeper. We can break it into 3 broad sections, not just metals, nonmetals, but 3 sections with specific names. Everything that's shaded in blue here is called representative elements. So the first column, the second column, and then over here, these 6 columns over here, those are all representative elements. That's not a very common term, but you should know it. Everything in the middle, here's a really important term. Everything that's here in yellow is called a transition metal. Not just a transition element, but a transition metal. Make sure you know that name. Everything down at the bottom, these 2 rows at the bottom in green, represent rare earth elements, or more specifically, rare earth metals. Now, this particular periodic table is laid out in a little bit unusual way because the element lanthanum really belongs at the beginning of that row there, and actinium belongs at the beginning of that row there. Because of that, the first row of the rare earths, starting with lanthanum, is really referred to as the lanthanide series, or the lanthanides, if you prefer. The second row, starting with actinium, is the actinide series. or the actinides, plural. So you could refer to that entire green section as rare earth metals, or more specifically, the first row is the lanthanide series, and the second row, the actinide series. Some more basic vocabulary about the periodic table. The rows on this table are actually referred to as periods, and I'm going to try to start using that term more often. So every row is called a period, and you'll notice they're numbered. There's hydrogen and helium in period 1, and everything from lithium across to neon is in period 2. Here's period 3, period 4, period 5. Period 6 does something a little funny. We have these two yellow fellows here, and then not shown, you drop down to lanthanum, go across the lanthanide series, then continue over here in period 6. Period 7 similarly has these two fellows here, then down to the actinide series and across, and then back up here. The modern periodic table, the latest version, has a bunch of elements that have been recently synthesized over there as well. So periods are the rows on the table, and currently we have 7 periods. The columns on a periodic table are actually referred to as groups. So these are columns on the periodic table. And there are 18 columns, and so the modern way of numbering them is simply to say 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 18 over there. Some questions on a web assignment may ask you to use an older system of naming those groups, and they were given a Roman numeral and a capital letter. For example, this was 1A and 2A. Now, there are different conventions for naming the transition metal groups. This one says 3B, 4B, etc., and then 3A and 4A continue over here. The inside cover of your Zundel textbook has the old convention and the new one, so if you ever need to use it, go look in the inside cover of the textbook and see the convention that's used there. One small detail, notice that we can now locate any element by its group number and period number. So if we wanted to talk about sodium, which is right here, we'd say it's in the 3rd period and the 1st group of the periodic table. Over here is neon. Neon is in period number 2 and group number 18. Now, the lanthanides and actinides down here have a small problem. Although they have period numbers, the lanthanides are in period 6 and the actinides are in period 7, they actually don't have group numbers. So none of these group numbers up here apply to the lanthanides and actinides. They apply just to the transition metals here. So none of these elements down here have group numbers. They have just period numbers. The periodic table can also be broken into families of elements. These are elements that have similar chemical properties. In the first column, and ignore these dark boxes, okay, focus on what I highlight here. In the first column, let me just change color. Starting with lithium right here, and all the way down to the bottom of that column, those are the alkali metals, alkali metal family. Right beside lithium is beryllium, and all the way down in column 2, group 2, we have the alkaline earth metals. So notice hydrogen, although it's in group 1, hydrogen is not an alkali metal because it's not a metal. We already know that everything in pink here is part of the transition metal family. Over on the far end of the table, we have helium and neon, all the way down to the bottom to radon, and those are noble gases. noble gases. They used to be referred to as inert gases, but we now know they're not inert, they're not completely unreactive, although they're almost completely unreactive. Beside them in group 17, starting with fluorine and going down to chlorine and bromine and iodine all the way to the bottom, those are your halogens. And those are the most important names, as well, of course, as the lanthanide and actinide series. However, sometimes, I've really never seen this on an AP exam, but the oxygen family, if you want to add one last name, is also referred to sometimes as the chalcogens. If you have to refer to any other column, for example, this column starts with nitrogen, you might just say the nitrogen family, the carbon family, the boron family. Okay, the problem there is that those families, those columns, contain nonmetals and significant numbers of metals. So they actually don't tend to behave as families. Notice that the alkali metals, the alkaline earths, the noble gases, the halogens, the chalcogens, and then everything over here, they all together comprise what we said earlier was representative elements. So that's it, I think, for the periodic table. We won't play a little video here, but we'll watch that in class. Those are vocabulary and names of different parts of the periodic table, as well as properties of metals and nonmetals. Things you definitely need to know for your unit test.